Alrighty, just like I said in the intro, the next step in this series is going to be the spec sheet. So basically, as I mentioned in the intro, this is where a good engineering project starts, okay? Like you need a good spec sheet is the key to a great project. You need a lot of specifications need to be very clearly and well defined in order for you to have a good idea. It gives you the proper constraints so that you're not like paralyzed with all the options you have. Okay, so that being said, we'll jump into all the things I listed that I think are worth noting. So then it'll give us what this is going to do is kind of constrain our search when we start looking for parts. Okay, so the first thing I've listed is output voltage. Of course, this is a 5-volt output. That's what we're going for. That's pretty typical USB. In fact, what I used was I went and looked. Here's an example of this is a 5-volt 1 amp Flyback power supply, right? It charges. There's a USB little charger. This was the inspiration for this project. So basically, I just want to copy and create something like this. It's not going to be this tiny, of course, because it takes quite a feat of engineering to do that. And maybe we'll get there one day, but right now we're just trying to get something that spits out 5 volts and 1 amp for us. Okay, so basically that's the reason I chose 5 volts. I think that's what a lot of things like your iPhone and anything that has pretty much has a USB port, that's what that power level is set out. Then the output current, this is the output current capabilities. It's not going to be spitting out 1 amp the entire time. Of course, it depends on the load, right? If you have a 1 kilo ohm load across it, then it's not going to be 1 amp. It's going to be much less than that. So of course the output power that equals 5 watts. If you multiply the amps and volts, then you get 5 watts. Makes pretty much sense. You know, it's math. It's just worth listing because of reasons, I guess. Okay, so the next important constraint is what about our connectors? Like, what are the interfaces through which the power is input, right? Because we need something to input power, we need something to output the power. So the input power connector I have selected is something that is called the IEC320-C14. So if you look on a lot of like laptop power supplies or computer power supplies, like if you have built your own desktop, the power supply unit will have a little inlet connector just like this one actually. So I didn't really have any rhyme or reason for picking this one other than I had really good models whenever I searched for it, so it was easy on the design side. It's something simple, and I don't yeah, it wasn't that was pretty much the motivation for that part. I know it can definitely handle our application, right? It can handle the input current and the input voltage that we're going to be giving it for our application as well, but just know this is going to be our input connector. The output connector, of course, is a USB type A connector. So again, I guess the reason I chose it is because this one has, it's like this, which is the inspiration for our project. The input voltage, now this is a good one to talk about for a second. And if you notice, I put 85 volts AC to 265 volt AC, and you're probably wondering, well, maybe what's up with that? So all around the world, if you look at those wall outlets, they all output actually at a different voltage, depending on like what country you're in and what the electrical standards are. Some places use 120, like in America, it's usually like 120, 115. Over in like Europe and stuff, a lot of places will use like 240 or like 204 or something, or 265. But pretty much all of the world, I think, operates in the range of 85 volts to 265 volts. And they might even be within that range a little by a decent amount. Like it might be like 100 to like 240 or something. But what we want to do is we want our design to be able to handle 85 to 265 volts, because let's say one of these outlets are having an off day and they're just not outputting as much. The voltage level isn't what it's usually at. We don't want our power supply to just blow up and like not work, right? Especially because we have the capability of designing something that can handle this. So we're going to design something that can handle this. That's for that reason. Another note is this is what's referred to as a universal AC input, because this can handle, like I said, pretty much all input ranges around the world. And so that's like a note for that. The last part I want to mention is the topology. So this is going to be flyback topology, which kind of makes sense if you've been watching the last several videos on my channel. I've been talking about flybacks a lot, but beyond that, you're probably asking, well, because this topology is flyback, I'm almost sure of it. But let's also talk about, well, why would anyone use a flyback in this case anyways? Like, what are the reasons for it? And I would say there are two major reasons for using a flyback converter as an AC to DC converter. Number one is safety. So flybacks have something what is known as isolated outputs, meaning the connections are the input and output are not actually physically connected. There's actually small there's insulated wire, and we're transmitting power basically wirelessly. Like if you've been following the last videos, you know we're using magnetic waves basically to transfer power and induce voltage. So what that enables us to do is create an incredibly safe power supply, because you can basically, they're literally not touching each other. So let's say something goes horribly wrong on the wall outlet side and things get shorted, and it's literally just like a giant it's literally like sticking a fork in the outlet. You ever played that game as a kid? So really bad things happen. People can get electrocuted because of that. If something starts malfunctioning, your devices could get destroyed because of that. So a lot of bad problems are solved by isolating the output, right? So you're basically protecting the low voltage side from the high voltage side. So the 5-volt output side is completely separate from the 5-volt from the high voltage side. So that the 5-volt output is completely separate from the high voltage. Let me say that in a different way that doesn't sound so confusing. The low voltage side is completely separate from the high voltage side. In fact, they use separate ground planes, aka separate return paths for the current in each side. Okay, so that's one major reason for using a flyback topology. The other major reason is that the component list requirement for these is extremely low. It's extremely simple. Like if you've been following along on those other videos, you saw there's only I don't know what, 4 or 5 major components. You have like the MOSFET, you have the transformer, you have an output diode, and then you have like an output capacitor. You have like 4, and then you have the controller. We'll call that a major component. So you have like 5 major components to work this thing. There's a bunch of tinier minor components, but they're insignificant in terms of size and cost, right? So you can create a very cheap, very tiny power supply with this topology. So that's another major advantage to this. With that being said, yeah, so I think that pretty much covers our spec sheet, and I kind of listed, I think it gives information of our motivations for this project, gave us some good constraints for when we started our search. Next video, we'll be getting into, I'll get into a system block diagram for actually how to design a power supply like this, and then we'll start taking a look at some data sheets and stuff like that. So stay tuned, please. And oh, please don't forget to like and subscribe for the YouTube algorithm. That really helps my channel out a lot. If you're learning something, that also makes me very happy. So